4, 3, 2, 1. We're live.
Welcome everyone to our Faces of Physics speaker series. So I'd like to thank our physics department for helping always be there for our SPS organization, our Society of Physics students. Of course, the College of Science and Marshall University, they've always been there to help out our Society of Physics students with outreach and events like this. I would also like to help acknowledge the American Institute of Physics that's also helping to co-sponsor this with the Society of Physics students here. We really appreciate the financial support that they've given us to have this speaker series. So I'd also like to thank Jackie Sizemore and Ellie White. They have done a fantastic job organizing this speaker series. They've been contacting people, they have been organizing the schedule, they have been setting up the links, they have been doing a fantastic job with this. So thank you, Ellie and Jackie. If you're interested in physics, not just specifically this talk, but if you are interested in this talk, I'm sure our speaker would be happy to stick around and talk with you afterwards. But if you're interested in physics in general and want to learn more about it, you can always contact me at marshall@marshall.edu or look at our website at www.marshall.edu/physics, and you can find out information about our department there. We have 10 faculty, 6 that are active in research, from theoretical condensed matter physics down to water filtration, solar cells. It's quite a wide variety. So at Marshall here, we have around 9,400 undergrads and around 2,800 graduate students. Marshall is an R2 designated university now. We have a BS program in physics, and we also have a master's degree program in physics and also a master's in physical and applied science. So within our undergraduate program, we have 5 areas. So if you have an interest in biology as well as physics, we have an emphasis in biophysics. We have an emphasis in medical physics, medical imaging, and applied physics, and our pure physics track. So if you're interested in any of those, or if you have lots of questions, just shoot me an email and I can direct you to the right person to talk to, and I can also try to address any questions that you have about our program in physics here at Marshall. So I think with that, I would like to thank our speaker before he begins, and just thank you for giving this talk tonight and donating your time. And with that, I think I'll turn it over to Ellie White.
Thanks very much, Dr. McBride, and huge thanks to everyone out there listening for tuning in tonight. So this will be the 6th talk in our Faces of Physics series, and I don't know about you, but I'm really excited to hear our speaker tell us his stories about adventures in building radio telescopes, and I'll be introducing him very soon. After the presentation, just like all the other talks, if you were here, you'll remember that we will have a Q&A at the end, and we welcome you to share your questions via the YouTube live chat, or you can post your questions on Twitter by tagging us with @MUPhysicsClub. If you enjoyed this talk, we hope you'll join us for future talks in the series. Our next speaker, slated for May 12th, is Bob Lutz, who's an engineer at NASA's Goddard Space Flight Center. And we'll be sharing more details about that talk as they become available to us. If you'd like to receive email updates about upcoming events, we will also be sharing a link in the YouTube description where you can go to sign up. So now it's my pleasure to introduce our speaker, Pranav Sanghavi. I've been fortunate enough to know Pranav for quite a few years. We first crossed paths when I was doing student research at the Green Bank Observatory in Pocahontas County, West Virginia, which you're going to hear a lot more about. And at the time, he was helping lead a program to teach middle and high school educators to build radio telescopes and integrate them with their classroom work, something that I think he's going to be telling us more about here in just a few minutes. Pranav is a radio astronomer with an undergraduate degree in engineering, and he's currently working on his PhD at West Virginia University. His research focuses on radio astronomical instrumentation to detect fast radio bursts, or FRBs, which are mysterious bursts of radio waves from the sky, and astronomers are still trying to figure out what they are. For his doctoral work, Pranav has built a prototype radio interferometric array at the Green Bank Observatory designed to work in tandem as a very large baseline interferometer, outrigger to the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, which is a fast radio burst detecting instrument. He also helps run the research experience for teachers, digital signal processing and radio astronomy, or RET-DSPIRA program, which I mentioned before, since the summer of 2017 to help bring radio astronomy to high school classrooms through building of radio telescopes from scratch, including and especially the digital signal processing side of things. He's completing his doctoral studies as he continues to work on data analysis from the prototype and the development of the upcoming CHIME fast radio burst outrigger to be built and commissioned at the Green Bank Observatory very soon. If you go on site and walk around like my family and I like to do, chances are good that you'll come across one of the cool projects that Pranav has built. We're so thrilled and fortunate to have him join us this evening, and it's my pleasure to turn things over to him right now. Thanks again to all of you for coming, and tremendous thanks to Pranav for making the time to talk about his work with us in the midst of his busy agenda.
Hi, thanks, Ellie, and thank you, Dr. McBride, and thanks, Jacqueline, for having me over here. I shall talk about building radio telescopes. I'll share a few slides, and it'll be a journey we'll take together. Is this visible to all?
Yep.
Right. Pardon me. Yeah. I am a PhD student at West Virginia University. I have been here since the year of 2016. And from the very beginning, I've been involved in building radio telescopes. And when I say building, I mean building from the very tip, the antenna, to the digital backend, and possibly do science with them. And I work, so I've been an engineer by training, and I wanted to be an astronomer and have since steered myself to a career in astronomy, and that has brought me here. So this talk shall mostly be everything I've done in the past 4.5 years in my PhD, all the general gist of all the projects that I've worked on. So a couple of disclaimers. This will be more of a journey to the destination. I shall keep the mathematics to a minimum, and we shall talk about what it takes to get to doing science, why we build the telescope, and the whole process of building it, and what you can do yourselves at home to take the similar science and engineering journey yourself. So what's this all about? I started my PhD and I had the choice of a couple of subjects. And very recently there had been a discovery, and at WVU at West Virginia University, just in the year 2007, where we discovered something that are now called fast radio bursts. They are bright and they occur for a very short period of time. When they're detected, they follow a certain pattern wherein the signal arrives much earlier at lower frequencies, and then it does at higher frequencies, and it follows an inverse square law. That is due to dispersion from cold plasma. The quantity dispersion measure from this particular phenomenon suggests that these events occur from outside a galaxy, which is mind-blowing. I mean, we see a lot of signals, but something that of this level of energy is something we had never seen before. They tend to happen just once. Since 2012, 2013 onwards, there have been publications every year with more and more fast radio bursts that are being detected by radio telescopes all over the world. So like I said, most of them happen just once. We know a few dozen repeat. And only one or two we are certain they repeat with a periodicity. So why do we care about them? They, like I said before, originate from outside a galaxy. And because of their extragalactic nature, they can be used as probes of what's between us and them. We have also localized a handful of FRBs to galaxies with cosmological redshifts. By cosmological, would imply that they're not gravitationally bound to our region. They move away from us because of the expansion of the universe. And because of that, we can study a lot about cosmology. All in all, they are quite enigmatic. They can be anything at this point, and we are detecting hundreds of them at this moment, and we are not certain to a high degree of precision that what physics governs them, and finding more about them could give us a lot of insights about a lot of things about the universe. But for all of this, we need to know where they come from. So how are we searching them? So there are lots of telescopes all across the world that have detected fast radio bursts. Um, the first one was detected in archival data from the Parkes telescope, which is the leftmost telescope in the pictures that I'm showing over here. There have been fast radio bursts detected by Green Bank Observatory, Green Bank Telescope, the Receiver Telescope. Sadly, Receiver is not with us at the moment. The single dishes, the large single dishes that exist, they're quite sensitive, but there are only so many FRBs can you detect with just one telescope, because the telescopes can be so big, and the field of view depends on how big you can make the telescope. The other way we've been detecting fast radio bursts is through interferometric arrays. We've got LOFAR on the right. We've got CHIME, the Canadian Hydrogen Intensity Mapping Experiment, VLA. The signals on these. So the way these work, real quick, and I'll get to the detail of how they work in or later on in this talk. They collect signals through individual elements on each of these dishes or along the focus, and they sum up signals in appropriate manner so as to synthesize a much larger telescope. And all of that this has been and all of these techniques are getting more and more accessible because of low-cost digital signal processing and new, more efficient techniques to do signal processing. CHIME FRB is one of these, and CHIME's awesome. It's quite special when it comes to fast radio bursts. Why I single out CHIME? Yeah, because I get to work with them. I have the opportunity to work with the CHIME FRB collaboration. So what is CHIME FRB? CHIME FRB is a sub-collaboration within CHIME. CHIME is the Canadian Hydrogen Intensity Mapping Experiment, and from the name you might wonder, why does the name have nothing to do with fast radio bursts? It's because when it was designed, it did not have anything to do with fast radio bursts. It is a cosmology experiment to measure the acoustic baryonic oscillation, which is a measure of dark energy in our universe. It is a cylindrical telescope. It is one of the many interesting cylindrical telescopes in the world. It has 4 cylinders, about 100-meter long, 20-meter wide each, and all of them, all along the focal line, have 256 dual polarized antennas. What's great about this is that this telescope always looks at the sky, and the sky moves in its field of view, and the field of view is quite large. It's around 200 square degrees. And the more sky you watch, the more FRBs you see. And primarily for this reason, and it's cutting edge sensitivity, CHIME has turned out to be a fast radio burst hunter. It has detected several hundred, at least the last published, in published literature has been mentioned there have been at least 700 detections, but we've detected several since then. Well, that's great. And you might say that we've been detecting fast radio bursts. Why are you building another one? Because you've got this amazing fast radio burst hunting telescope. Why should we care about a new one? So the problem is, CHIME, even with its best synthesized beam, can only see so much up, can see a region of the sky which has several galaxies in it. So we cannot for certain know where from those galaxies these FRBs come from. And another thing which I mentioned before is fast radio bursts do not repeat. Most of them, a large chunk of them, just do not repeat. So if you were to see an event from one instrument and you just cannot follow up with other instruments, you lose a lot of information that you could potentially get from several coincident detections. Additionally, like I said before, if the telescope can only be so big, the resolution of the telescope is inversely proportional to the diameter of your collecting area, the dish. And you can only make a telescope so big, it is restricted by the cost. It's restricted by how strong a mechanical structure can be of that shape. So what do we do next? We try to do interferometry. And since we care more about localization, when we want to localize fast radio bursts to a very specific tiny sliver of the sky, so that it could be localized to an individual galaxy, we want to do something called very large baseline interferometry. So I quickly glanced through what are interferometric telescopes before. I'll again quickly glance through it. So I'm trying to avoid mathematics as much as I can. But the way this works is you mathematically, I would like to say sometimes, is you add all the signals to make one single big telescope, and the resolution of that synthesized telescope that you built by summing all those signals cleverly is inversely proportional to the distance between the farthest elements or dishes, if you're using dishes. So if you want to really have a very high resolution, you place your elements as far as away from each other as you can. That's something a lot of cool telescopes do. You might remember the movie Contact and the Very Large Array that they found signals from aliens in, but not aliens in our case. Definitely not, for sure. 99%. Okay. Yeah, so how does this interferometer work? So if we consider this big dish, what essentially happens is light, it reaches a reflector, it's collected by the antenna, and that's connected to electrical voltage. Now, if we sample parts of the dish and collect the, I'm sorry, this is going a lot faster than I hoped it would, but this will loop back in. Yeah, so you collect the light from different parts of that big dish, and you sum the signals together, and you essentially it's equivalent to getting the dish of getting light from that one big dish. Sorry. Yeah. However, so considering you have those sample spaces from those dish and you bring them to a ground level, you also compensate for the extra time the light takes to reach the dish on this place on the ground. You get a signal that is equivalent to having a signal from a giant dish. Now we have these two telescopes, and we call the distance between the telescope a big baseline. We place these telescopes at a very large distance, you get a very large baseline interferometer. And this very large baseline, it's almost if you've got a large baseline on the other sides of the continent, you've got a very big telescope the size of the continent. So yes, this is the idea which we had essentially. We use the superior FRB hunting potential of CHIME to detect as many FRBs as we can. And we also have the secondary telescopes called outrigger very far away to keep recording data. And as soon as there's a detection on CHIME, we save that data at the same time at the outrigger. Now we use the VLBI techniques to really localize the FRBs that happen just one. So we started with a bunch of prototypes. there's a small baseline prototype right by CHIME called the CHIME Pathfinder, the experiment that was used to test the technologies for the CHIME telescope itself. And a lot of the technologies that was involved to build these outriggers were tested there. And also at the Algonquin Radio Observatory. Something I forgot to mention before was the CHIME is at the Dominion Radio Astronomy Observatory in Penticton, near Penticton, British Columbia. And one of the telescopes at the observatory, along with one of the telescopes at Algonquin Radio Observatory, were one of the first very large baseline interferometric measurements ever made. So yeah, so there's another outrigger prototype at ARO, and a third one, which is the one which I helped build, which I've been calling TONE. It used to have an acronym. That acronym didn't stick. I mean, TONE doesn't stand for anything anymore. It is just following the musical metaphors that CHIME and the CHIME collaboration has been following within the project. So TONE, it's a 6-meter dish array at Green Bank Observatory, and I shall be talking a little bit about what went into building it. So before that, let's just quickly talk about what happens at the outrigger prototype. So we've got these pulses from FRBs. They are detected at CHIME, and as you can see in this nifty animation, it gets detected at CHIME, it saves the data at CHIME. It takes a little fraction of a millisecond to reach the other outriggers, and it saves the data within a buffer, and we get a signal through the internet, and the custom software saves the appropriate data that was received at the outriggers. So what the data kind of looks like. So what kind of information do we collect? The information that we work with, first, we need to know as precise as we can of the locations of all the telescopes, the precise time at which the data was taken, and the data itself. So I'm showing the data from, this is real data from real telescopes, from the telescopes, what I'm saying. So to the left is the data that we're getting so far to test our algorithms and our system is from the Crab pulsar. We get occasionally giant pulses from the Crab pulsar that are extremely bright, which can be analogous to what an FRB could be like if it were to reach our detectors. So we've got data from CHIME and we've got data from TONE. I am glossing over a lot of complex math that takes place at both of these locations. As you may have seen before, these are interferometric arrays. You've got multiple antennas, and we sum all of these antennas in clever ways to create one single beam in the sky, so that it behaves like a much bigger dish, a much bigger single instrument as we are. So we get these, and we do a mathematical operation called cross correlation. So what happens cross correlation? This is again using real signals. I'm doing a very simple cross correlation of 2 time streams. So we've got our signals. You can see the blip that happens in the middle of the 2 time streams. Those are when the pulses from the Crab pulsar reached our detectors. Just from the axes, and the axes are in units of 2.56 microseconds each. So that is how fast we are sampling our data at the telescope. So it might seem like they arrived at almost the same time, but when we cross correlate, we see that the signals cross correlate. They seem to be similar in these 2 signals. They seem to have a lag. The jargon used is called lag, for about about 0.00189928 seconds, and that's roughly how long it takes for light to travel a little bit more to reach tone than it did CHIME. And that number is dependent upon the position of the source, so where where the signal comes from, and the distance between the two telescopes. So once we have this time measured by very precise numbers, we can calculate where the signal can come from. So building this, so that's the fun part. As some other astronomers and physicists and theorists might say that it might not interest them much, but this is it's another kind of beast, trying to build your own experiment from scratch and make sure it works. And when it works, the feeling is something else altogether. So we had planned 12 dishes in a regular array pattern, just regularly placed in a rectangular grid. We used off-the-shelf 6-meter dishes because they're really inexpensive and you could just they just work, and they can be used. So why did we choose Green Bank as our as the site of our outrigger? Mostly because a lot of you might know Green Bank is in the middle of the National Radio Quiet Zone. And more obviously, it's because it's the site of the Green Bank Observatory. Green Bank Observatory is kind of a special place for me. It has been very important for me to learn about radio astronomy as throughout my PhD. And those residents of West Virginia who do not know about Green Bank, I highly recommend you visit. So Green Bank Observatory, it is the site of the Green Bank Observatory, and it has a lot of expertise and technical support that one can get for radio astronomy with respect to building large structures, to designing infrastructure for radio astronomy. All of that is available on site at Green Bank Observatory, and it makes it an invaluable place for a new instrument. And the most obvious reason is that it is really far away from CHIME. It's around, pardon my metric, it's around 3,371 kilometers away, which allows you to give milli-arc second localization, which is really good. It's I should have done an order of magnitude thing, but take my word on it. You can localize bright FRBs in nearby galaxies where they come from. So, which is cool. Yeah, so the whole process of building it, it has been a journey. We started building it in the year of we started building in the year of 2017, but there's few caveats when you're trying to build a telescope in the radio quiet zone, especially on site right next to the Green Bank telescope that you see in the background over here, is that you're not allowed to use power tools. You are supposed to just do it yourselves. You could possibly work on building your telescope during the couple of weeks where the telescope is being painted. However, world economics and shipping of the different parts and just nature in general just doesn't always agree with your strict schedules. So sometimes the way I worked with is a rotating second helper. I built all the dishes that are already up there, and we come up with a fun plan to assemble all of these. So each of these dishes are at least more than 300 pounds. So around 300 to 400 pounds at least. And you work when you can work because, like I said, there's only so many openings when you can actually be over there. The photos that I'm showing was on a particularly rainy day, and I was wearing a trash bag so I can just continue working. And there was a lot of deer poop. but it was still fun. We were able to build at least a few dishes. But before we built a couple of dishes and we had to go back to WVU, there were a couple of windstorms. Like I said, in large projects, apart from being clever, you just got to be really lucky. And we got really unlucky. Despite all of our efforts, a couple of dishes just flew away, like Mary Poppins. Quite literally, they were just like huge sails in the wind. At least one of them showed signs of being airborne. So we lost 2 dishes that we spent so much time making. But that didn't deter us. We kept going. And we built more dishes. You can see here in this video, this time-lapse video of this excellent staff at Green Bank Observatory mounting the dishes to their poles. It has been an experience doing this. This is unlike any other. Most radio astronomers, not a lot of radio astronomers get a chance to do this. The photo on the right is actually my advisor, Kevin Bandura, me, and one of our undergraduate students, Jacob Haney. So at the end of the whole ordeal, we were able to assemble 9 dishes out of 12, and 2 of them were blown in the sky. 1 is still left to be assembled. And this was completed by November 2019. This was just about the time it had started to get real cold. That was a success as much as we wanted it to be, and as much nature allowed us to be. Then the other part, what I just talked about were the reflectors, the buckets that collect and reflect the light. Now the actual collector that converts the light energy to electrical energy are our antennas. These antennas were designed to be sensitive over 400 megahertz of bandwidth. They go from 400 megahertz to 800 megahertz. Like I said, these were designed for CHIME, and these are the frequencies. CHIME was interested in observing for the cosmology. The variant of the antenna design we used were for one of the revisions for the HIRAX telescope. The HIRAX telescope is another big telescope under construction and in South Africa. My advisor, Dr. Kevin Bandura, is an active member of that collaboration. On the right, you can see the next step of our signal chain, where the amplified signal from the antenna goes to our radio frequency over fiber. It again converts it to light so that we can send the signal from the dishes to the digital backend. Again, this is quite interesting. So the radio frequency of fiber chips of these devices were designed at Carnegie Mellon University by Dr. Jeffrey Peterson's group. Again, engineering and science is an iterative process at times. There's so much your simulations can teach you, but sometimes in the real world, certain factors can cause things to break down, and all of them did break down, and which had to be sent back for a revision. And we got another version of these RF over fiber connectors by the end of by the time we were ready to deploy these. Another fun thing that goes into real science is to see how hard your equipment is to the aforementioned forces of nature. As you can see, we are testing our antenna case for rain. If all the many protections to save the antenna from the weather actually works, and the best way we could think of was just dump it under a stream of water. Surprisingly, nothing got broken, and our clever methods to save our antenna from the rain actually worked. A lot of these, and this is something I will keep on stressing throughout. It involved a lot of people. I actually helped train an undergraduate student to test and assemble these antennas. He even came up with a way to a jig of sorts to assemble these antennas really accurately. That's Jacob from the picture below. So a lot of learning goes into all of this. And so once you have the antenna and you've got the signal coming back in, now you have the analog signal. So the next part of a signal chain goes to the digital backend. The digital backend, what we use is this beast, the state-of-the-art device which we've been calling the ice board. It has two very key components that we really care about. The first thing, the one in the red that is up top, it's the digitizer, the analog to digital converter. It takes 16 analog inputs and converts them to digital signals. In the olden days, and maybe some of you have been to Green Bank and to the 40-foot telescope, they used to use analog circuitry or even chart recorders to record the data. But most modern telescopes use something called field programmable gate arrays, or FPGAs. They are programmable chips. So they're like your microprocessor or your computer, or the chips that do your computations on your cell phone, except it is very specific to an application that you use. And what's special about them is that they can be programmed on the fly. That's why they call them field programmable. There are a bunch of logic gates, registers, counters that can be wired through a program that you write. And so you get a processor that is specific to what you want to do. And the specific task that we want to do in our telescope is to convert our digital time streams to channelized voltages. You want to convert, like I said before, our antenna is sensitive to 400 to 800 megahertz. So we want all of that information discretely in different channels. So it does something called polyphase filter banks, a special kind of fast Fourier transforms that converts your time streams to different frequency channels. And it also does lots of fancy stuff when it comes to networking and sending all of those data. It has a little computer on board that lets you interact with all of these components and get metrics and whatnot. This was developed by the folks at McGill, and again, this is done by a lot of people from all over the world. It takes more than a village. It takes a lot of hard work to get something this sophisticated running really well. So next step. So we now have digital signals. Like in the picture that I'm showing above, this is the RF over fiber receiver that converts our light that we got from the antenna back to analog signals. And then below over here in the silver casing, it is the FPGA that I just mentioned before, the ice board, and then that's sent to the recording node below. Now, this recording node below is a very special computer. It's designed to just save your data. It has 500 gigabytes of random access memory. And the way it does our data recording is it continuously writes your data into a ring buffer, wherein it starts recording until it fills up the 500 gigabytes and rewrites over and over again until it gets something called a trigger. A trigger would be a detection at CHIME, which will have our custom software save a slice of that ring buffer to disk. The data rate is obscene. We just cannot keep writing things to disk, and a lot of custom software has been developed to make this happen. And the way this triggered, just to visualize what actually happens, maybe you might remember from the Oscar-winning movie series Lord of the Rings, where Gandalf makes Pippin light the beacons, and all the beacons all along the mountain reaches Gondor, and then Gondor responds. So it's kind of like that, except it goes much faster. The speed at which the beacons are lit are given by how fast our internet speed, like our connections are. We have two servers which are these bonfires on separate peaks, and once we lit one of these peaks and we see it on the other one, it acknowledges it, and then we save the data. So yeah, so all of this is on, we spent a lot of years with a lot of collaborators to actually get this going. Now we just need to wait for what I've been calling a space boom, an explosion. It's not really an explosion, but it's this enigmatic event. We want a really bright one to occur, mostly because Stone is not as big as CHIME. So to be able to be seen at both of them together, it needs to be of a certain brightness. However, we can also get more if we build a larger telescope, which we are. No, that's not a secret. It has been planned. We will build a full-scale outrigger, which would be much like CHIME, but slightly smaller than CHIME, at Green Bank Observatory, along with a couple of other places. And a lot of work is already ahead into the development, including the logistics and designing the digital backend. Again, custom software that would handle such huge specialized data. So you might say that this is really something. It seems exciting. You get signals from across the galaxy. I like to co-opt Green Bank Observatory's public relations slogans. The universe is whispering to us, and indeed, these are very relatively faint signals that we listen to and learn a lot about our universe. And a lot like most of modern science, like I've mentioned before, it requires a lot of work from a lot of people from all over the world, and not just one discipline. You've got engineers, you've got mathematicians, you've got statisticians, you've got physicists, you've got cosmologists, all working together to make this happen. It's like within the CHIME collaboration, these are the several universities where we've got our members from. And these are just the affiliations. The people working in those universities are from all over the world. So you might think this is cutting edge science, only science people can do. And yeah, but you can do this too. And that's where I will steer this to another telescope, where you can build at your home, in your garage, or at your school, and or in your backyard, or with just your cool friends. So this is another project I've been working, as Ellie had mentioned, with the high school teachers, where we build this little radio telescope. I'll quickly talk about this program. It is the RET program, the Research Experience for Teachers site. It's at WVU, West Virginia University. We've had high school teachers every summer since 2017. And the way we did stuff was we spent 4 weeks at WVU and 2 weeks at Green Bank Observatory. And we learn about digital signal processing and radio astronomy and build a telescope from scratch. Our telescope is a little different from the one I'd mentioned before for radio astronomy, for the one that I've been working on. It is sensitive to the neutral hydrogen. It works at 1.4 megahertz. 1.4 gigahertz, my bad, sorry, at 21 centimeters. So that being said, I'm just going to go, I might have dumped a lot of information, so I'll just quickly go through what exactly is happening in a radio telescope. So we've got an antenna. An antenna converts energy. It converts light, electromagnetic radiation, to electricity. Then you've got analog electronics, which massages your signal. It makes it brighter. It filters out things you don't want. And then it sends to a digitizer. A digitizer converts your analog signal to a digital signal, and that be sent to some kind of computer to process it. So your antenna, in this case, are these horn antennas. Now, what happens with these horn antennas? They have a little conductor. It is actually the antennas inside this can. And it converts light to electrical energy. The horn does the process of collecting the light from space down to the antenna really efficiently. The electrons, once light hits the antenna, electrons move, and the shape of the antenna dictates how well those electrons move and at which frequencies they will. Hence, you say it is tuned to a certain frequency. These horn antennas you can build with any supplies you can get from home improvement stores. These were bought from supplies from Lowe's. Yep, for less than $50. A cool thing about this particular antenna is it's not unlike the very first antenna used by Dr. Evan and Purcell to detect neutral hydrogen in the galaxy for the very first time. And you can see the horn at outside the Jankski lab at Green Bank Observatory. The building of the horn we did at WVU at our makerspace with the high school teachers. This was quite an experience for all of us. The next is analog electronics. Analog electronics, it's, I would say, our biggest bottleneck in this particular situation because it involves a little bit of complicated electronics, which might not be accessible to everyone. However, the hardware is open source. You can order the boards online and the components, assemble, solder them together if you're up for it. You can also purchase mass market ones from companies everywhere. I think the ones we have at WVU that we've developed is much better, but I'm biased. So yeah. And then finally, our digitizer and what we use for our software for this particular project and what you can use. We use something called software-defined radio. And it's not unlike anything what I've mentioned for the very fancy project. The AirSpy situation, it's called the SDR dongle. What it does is it converts analog signals to digital signals, which is exactly what I had mentioned over here. This is this guy, except it's a lot more inexpensive, slightly less sophisticated, but it essentially performs the same function. And all the custom software that I mentioned, GNU Radio lets you make your own custom software. We worked with high school teachers, and even high school teachers in a program have made custom software to do radio astronomy. And all of that, again, is open source, and you can access them at these websites, which you can email Ellie or I, and we can share this with you. So yeah, the cool thing is this is not restricted to radio astronomy. An antenna is the basis of modern life. Our Wi-Fi signals, our cell phones, everything that we use that facilitates modernity at the moment relies on digital signal processing and antennas. A large chunk of it, for sure. And you can learn a lot about it if you want to, say, grab satellite imagery from NOAA satellites. You can do that. You can, if you live close to naval stations, you can even get telegraph newspapers, depending on where in the world they're broadcasting. So it opens up an important aspect to science and engineering by just doing this on your own. So talking about the hydrogen, which we use this telescope to do, like I mentioned before, it's a 21 centimeter. It is from the hyperfine transition. It's a spectral line that is everywhere because it's one of the most abundant elements in a universe. It emits at 21 centimeters or 1420 megahertz or 1.42 gigahertz. Because of Doppler effect, the relative velocity at which the hydrogen gas moves to us, it redshifts or blue shifts the signal, and it gives you the spectral line at not exactly 1420 megahertz. It's ever so slightly different. And those correspond to the speed at which they do. If you see multiple peaks, if you're looking at a galaxy like in this image that I'm showing you, it's again using from our software that we use, GNU Radio and all of this. Those multiple peaks are from different arms of a galaxy. That's something we just do not see from our just eye. We can, however, see this using radio astronomy. You put it all together and you can make an observation of the sky. I have this wonderful video of a couple of our teachers. It's real quick of taking a quick observation of the Milky Way galaxy. Yeah. Yeah, so as you can see, by pointing at a certain direction in the sky, you see the red line is where it should be, 1420 megahertz, except it's a little bit shifted in frequency that corresponds to the relative velocity at which the galaxy is going. And you can see, you can just do this in your backyard. You can see that this is at a random parking lot in Morgantown. Yeah, so, pardon me, this is taking a minute to just go. Yeah, so there's lots of fun things you can do with this telescope, just which some cost of components is, I would say, less than $200 if you want it to be. And you can map the whole Milky Way galaxy over several days in clever ways. This is an old plot that we made with multiple telescopes pointing at different sections of the sky and collecting data for 24 hours. The empty spots you see are parts of the sky that are below the horizon, and the bright orange is our galaxy. The other things you could do with this particular telescope, it's like I said, the shift in frequency corresponds to the velocity, the relative velocity at which the mass of gas is going relative to you. And this is roughly how dark matter was discovered. As you can see, the different observations, they tend to flat out as you point away from the center of the galaxies. And this is data taken by high school students by one of our physics teachers who was part of a program, John Mackis, and from North Carolina. And you can see different observations done for different parts of the year, different times of the year. And if it weren't for dark matter, the plot would look completely different. It would the velocity would lower as you go away after it peaks at a certain point. There's a cool thing you see over here at certain the measurements taken at different times in the year. You can see there's an offset. That offset can be attributed to how fast Earth is moving around the sun. And yes, that's something you can measure too. So as Earth moves around the sun, it to the hydrogen gas in the center of the galaxy, you are moving at a different relative velocity. So if you were to point this telescope at the center of the galaxy, you can measure how the the frequency is shifted because of Doppler effect, because at the different points in our orbit around the sun. So this was an experiment done by Tad Herman from New York State. He was also one of our high school teachers of the DSPIRA program. And he took this data throughout the year in his backyard. He just point at the center of the galaxy, collect the data, and you can see how well it matches with the predicted shape. There's one thing you might ask as to why is it offset from what the predicted motion should be? And that's, one might guess it could be from another radial component of our velocity. And that's because we're also moving around within the galaxy itself. And that is what is manifested in this radial component. So all of this is from just in looking at invisible signals in the sky. Radio astronomy is indeed an enigmatic field of astronomy. It has the least pretty pictures. It can have pretty pictures, but it tends to tell us a lot of things then from just the basic physics and engineering principles. We're really fortunate to be able to do all of this. Like, for example, just being in a society where we invest in science and technology to advance such cutting edge methods to learn about a universe. We were even able to do this in the time of a pandemic, which is again lucky. And it takes a lot of effort from a lot of people and make science possible. So yeah, you can do everything from look at explosions from other galaxies to learn mysteries about your own galaxy with radio telescopes that you build. And that's roughly what I have to talk about today.
All right, thank you very much, Pranav. Very cool stuff. Let's just go ahead and hop right into the questions because we've already got quite a few so far. So first one, back when you were first introducing FRBs, we have Parashuram Dora wants to know, does the expansion of the universe affect the repetition?
The expansion of the universe is not that I know of. So the expansion of the universe would factor into something what we call the redshift. That is the signal that we get. It seems to be, it moves away from us and it comes at a much lower frequency than it actually is. However, we just see one of the FRBs and I would say no, it doesn't really factor into repetition. Yeah, it would factor into the large scale structure of the universe, but that is completely different from the phenomenological processes that cause FRBs.
All right, thanks. Apostolos said, did you mention 700 plus observed FRBs? The transient name server FRB catalog contains 306 events, including repeater bursts. Is there a different database I'm unaware of that contains more bursts?
We are in the process, the CHIME FRB collaboration is in the process of releasing a catalog. It should be out in the coming months. It's just we're in the process of verifying, vetting, and also having our work peer reviewed. And once that's done, we should be having a full catalog sent out.
All right. Okay, moving on down the list. Let's see. Another question from Apostolos. Have these RF over fiber PCBs got an LNA integrated at the SMA input?
Yes, there is an amplifier.
Okay, short answer to a short question. So not a question, but Haley Wall says, this is so cool. I think this was when you were talking about the ICE boards. We always talk about the science that's done with instruments, but it's amazing to learn how the instruments themselves are built. And then later they said, amazing talk, Pranav. What's your favorite thing about your research, or what has been your favorite part about this project?
The people I get to work with. I want to say that I get to learn about something nobody knows. That actually happens. There's sometimes I work with these instruments and I find an event in the universe for which I am the first audience. And that seems cool, but all of that is fleeting. What actually is the favorite part is I get to work with some of the most exceptionally clever people from all across the country and the world. And I learn a lot more than I ever thought I would. It's humbling, grounding, and also good for science. Like the discussions that you do with your colleagues, it's invaluable.
It's good to hear. All right, just so everyone knows, we are accepting donations. If you make a donation to SPS, you could be entered for a chance to win a Yeti cooler, 45 quart River Green Yeti cooler. So if you're interested in making a donation, you can go to the physics page in the description of this video and find Dr. McBride's email address or my email address on the SPS page. Well, is there any closing remarks from Dr. McBride or Ellie?
I just want to say thank you for your time and your talk. I think it was very good, and we did get a lot of good questions from it. So I do appreciate you spending an hour with us and telling us about what you've done for the last 4 to 5 years. Very exciting stuff.
Thank you, and thank you for having me. And anybody in the audience or wants to build radio telescopes, hit me up. I got you, fam.
We did get one more question. Are you okay with answering another one? There's a bit of a lag between the video and
yes,
so
I am aware of that. I actually checked that before.
Okay, yeah. Okay. So PhD electronic can get to work in astronomy or education in astronomy. So I think there, yeah.
So my PhD is in electrical engineering. I'm affiliated to the Statler School of Benjamin M. Statler School of Engineering and Mineral Resources and the Lane Department of Computer Science and Electrical Engineering. But most of my work is all over. It goes from, like I mentioned, everything I've mentioned, I've done, from the engineering to systems integration to working with actual science, the astrophysics of it. So again, it's not trivial, at least even for me, it wasn't trivial trying to go from engineering to astronomy. And again, like a part of it seems to be like focused on science education, the DSPIRA project. Most of it is, like I've mentioned before, a lot of luck happens into this, but otherwise, talk to your local university professor. I called Dr. McBride and I was like, hey, I'm interested in this. And they're more than happy to direct you into the different corners of the dark side, as I like to call it.
Yes, I definitely agree with that. Contact me if you have questions.
All right, Ellie, did you have anything left to say?
Yeah, I just wanted to thank Pranav again. That was a super cool talk. And also I wanted to repeat something you said. Green Bank is amazing, and for those of you who are watching who maybe haven't been, then definitely try and make a trip. Their science center isn't currently open, but they're having walking tours. So you can actually go walk around the site, and if you kind of stray off the typical tour a little bit, go behind the big telescope, you can actually see Pranav's telescopes for yourself. So it's really
hard to miss.
All right, thank you so much again, Pranav, and thank you to everybody that has come to listen to him talk today. We had a really good time, and we look forward to seeing you next time. Bye-bye. All right, the stream has